Welcome to Lecture 6.3, Solving PDEs with Laplace Transforms. Let's begin by introducing the Laplace transform. I expect that many, if not most of you, have seen this before from your class on ordinary differential equations. That said, I will not require or assume such knowledge. First, we need to consider a function f that's defined for positive values of t, and it has to have exponential order, which basically means that it doesn't grow faster than an exponential function. So here's the formal definition, but just think of it as no bigger than an exponential function. Okay, now suppose that f is a real valued function that is piecewise continuous and of exponential order. Then the Laplace transform of f is the following. Before I describe this integral, let me give you the big idea. So the Laplace transform inputs a function, think of it as time, and it outputs a function of a different variable, s, which we can sometimes think of as frequency. So the Laplace transform is an operator. It's a function of functions, and it's a linear operator as well. And here's how we define it. So the Laplace transform of little f, which is a function of s, which we abbreviate as capital F of s, it is the integral from 0 to infinity of f of t times e to the minus st dt. So we are basically integrating out the t. So what we get only has an s in it. And this is a little bit weird to think about. It takes a while to get used to, and those of you who have seen it, you probably remember from your differential equations class how it just didn't click right away. You have to practice it. But practicing it is not really the focus of this class. We're not going to do all the fun and interesting things that we did in an ODEs course, but we will basically just see how we can, as an overview, we will see how we can apply the Laplace transform to a PDE to reduce it down to an ODE, which makes it easier to solve. Okay, so let's go back to your differential equations class and revisit some of the basic properties of Laplace transforms. So the theme here is that if we know the Laplace transform of a function in the time domain, and then we modify it, like we take a linear combination or we shift it or dilate it or take the derivative, then we know how to compute the Laplace transform in the frequency domain without having to do the integral from scratch. So it's usually a modification of the Laplace transform of the original function, which is capital F. Okay, so Laplace transforms are linear, which means that if you start with a linear combination in the time domain, c1f1 plus c2f2, and you apply the Laplace transform, then you get c1 times big F1 plus c2 times big F2 in the frequency domain. So this should not be surprising because integrals are linear operators, and a Laplace transform is defined in terms of an integral. So you can pull apart constants, you can break apart sums. The next is a shift. So if you shift in the time domain, then that corresponds to multiplication by an exponential in the frequency domain. And conversely, if you have a function f of t and you multiply by an exponential in the time domain, then that corresponds to a shift by c in the frequency domain. So there's this nice duality property of time or phase shift versus multiplication. Similarly, dilation. If you dilate in the time domain, so f of ct, then in the frequency domain, you get the opposite of that. So you get 1 over c times f of s divided by c. So think of multiplying by c here. Think of it like a sine or cosine wave as increasing the frequency by c. And in the frequency domain, you're doing the opposite. You're dilating it by c. The next two properties are also dual, sort of like how the shift versus multiplication by an exponential are, and they are probably one of the most important properties of Laplace transforms, not just from ODEs, but for PDEs as well. And basically, they say that multiplication in one domain corresponds to differentiation in the other domain. So to begin, if you take the derivative in the time domain and then compute the Laplace transform, that corresponds to multiplication by s in the frequency domain. So the Laplace transform of the derivative of f is s times the Laplace transform. And then you have to subtract off what I call this fudge factor, f of 0, which is just a constant. And conversely, if you multiply by t in the time domain and then compute the Laplace transform, and you just get the derivative of the Laplace transform times -1. So you can extend this, that if you multiply by if you multiply by t squared in the time domain, then that corresponds to the second derivative in the frequency domain times a +1, because you can multiply by -1 twice. Finally, also important in this lecture is convolution. Now, you'll be fine if you've never seen convolution before. I will not assume that knowledge, but I assume that most of you have. And what's useful about this is the unfortunate property, but not surprising, that if you multiply two functions together in the time domain, f1 times f2, and you compute the Laplace transform, you would hope that it's multiplicative, that you get f1 of s times f2 of s. But unfortunately, this is not the case. And it shouldn't surprise you that it's not the case, because you know what else is not the case? If you integrate f1 of t times f2 of t, it's almost never the case that you get the integral of f1 of t times the integral of f2 of t. So you should never expect this for general integrals. So of course it's not going to happen for Laplace transforms. But amazingly, something very close to this actually does hold. And that's what convolution is. If you not multiply your functions in the time domain, but if you take something called the convolution, which is a way to multiply them together, and we'll go over this shortly in a few slides. We're going to devote an entire slide to this because it is important. So if we do this convolution product in the time domain and take the Laplace transform, then we get the product of the Laplace transforms. And conversely, if we take the product of two functions in the time domain and take the Laplace transform, then in the frequency domain, the answer is just the convolution of the Laplace transforms. So this is also one of these dual rules. In other words, there's a duality here, like there is with differentiation and multiplication, and there is with shifting and multiplication by an exponential. Let's now do an example of how to solve an ODE with a Laplace transform as a warm-up for solving a PDE. Let me first give you the big picture. So for all of these, we start with an initial value problem, and here's one right here, a differential equation with initial conditions, and we would like to solve this. So the solution we would like is to figure out what function u of t, and there will be a unique one because we have two initial conditions here. Now, what is the solution? So let me write that. What is the solution u of t? So of course this one we know how to do directly. This is uninteresting. But just for the sake of seeing the process, let's go through this motion with how to do this with the Laplace transform. So we compute the Laplace transform, and when we do that, what we will get is no longer something involving derivatives, but something involving multiplication. So we will get an algebraic equation involving in capital U and the variable s. So what we can do is, this is algebra, we can solve. So we can solve for u as some expression. That's algebra, that's easy. And then all we have to do is figure out how to undo that. So this is called the inverse Laplace transform, and we need to figure out what function of t has this function as its Laplace transform. And there will be one of them, and that function is the solution. Of course, we don't need to do this for this function, but one reason why this is so useful is if our forcing term, instead of being 0, what if instead we had a function like a square wave? So this would correspond to, or models simple harmonic motion, a mass spring system, where the forcing term is a square wave. Now, all of a sudden, we cannot use calculus for this. Our calculus breaks down. So we have to use something else. Now, I'm realizing as I'm saying this that I've showed you how to do this with Fourier series, and I guess that's great, but when I teach differential equations, and when most people do, they haven't learned that already. So this is an alternative way to solve a differential equation where your forcing term it maybe is piecewise, and it actually has different pros and cons. And I won't go into that, but I will refer you to my differential equation class when we solve differential equations with Laplace transforms. So take a look at those videos if you want to learn more about this. Okay, so now back to solving this problem. So the first thing that we always do is we compute the Laplace transform of both sides. So the Laplace transform of u double prime plus u equals the Laplace transform of 0. So both sides of this we apply L to. And so this left-hand side is the Laplace transform by linearity of u double prime plus the Laplace transform of u equals the Laplace transform of 0 is 0. So this first term here, two derivatives, that turns into multiplication by s squared times capital U minus s times u of 0 minus u prime of 0. I won't go, I showed you the formula for the Laplace transform of derivative in the last slide. The one for the second derivative is what you get when you apply that twice, and I won't go over the details of why this is it. Again, go back to my ODEs course if you want to know more. So this is just that term there. So let's put parentheses there, and then the Laplace transform of u is big U equals 0. So now we go back to these initial conditions, and this one is 0. So that goes away, and this one is equal to 1. So when we simplify this, we get s squared u plus u minus 1 equals 0. So let's simplify this. This is s squared plus 1 times u equals 1. So we get that u is 1 over s squared plus 1. So this is a function of s, but I think that's understood. I'm not going to write that. So what we did here is we started with this initial value problem. We applied the Laplace transform. We turned it into this algebraic equation. Let me write that down. S squared plus u minus 1. S squared u plus u minus 1 equals 0. We solved that. U equals 1 over s squared plus 1. And the question is, what function has the Laplace transform equal to this? And it turns out it's sine of t. And again, the derivation of this is an ODEs course, but if you go to Wolfram Alpha and you just type this in, it'll probably guess that you want an inverse Laplace transform and give you sine of t. Or you can type in inverse Laplace of this and it'll do it right away. But usually what happens is we use tables or computer software for inverting this. Since our goal is to apply Laplace transforms to solve PDEs, we need to know how to take the Laplace transform of a multivariate function. And your guess is probably correct. What we do is just treat all of the non-time variables as constants. So in our setting, we will look at a function u of two variables, x and t, and its Laplace transform is defined as follows. So L of u is going to be a function of x and of s instead of t, and we'll usually write that as a capital U of x and s. And again, we just treat x as a constant, and we multiply by e to the minus st and integrate out dt from 0 to infinity. Not surprisingly, the Laplace transform turns t derivatives into multiplication, and it leaves x derivatives unchanged. Let's start with x derivatives first. So if we're taking the x derivative of a function, then we're just ignoring t, treating it like a constant. So the Laplace transform of the x derivative of u is just the x derivative of the Laplace transform. Similarly, if you take two derivatives, the Laplace transform of uxx is just the second x partial of the Laplace transform, capital U, and so forth. Now, t derivatives are a different story. The Laplace transform of ut, once again, we just treat x as a constant, so it is s times the Laplace transform of u minus the initial condition u of x 0. The second derivative is analogous, and it's derived by noticing that utt is the t partial of ut. So just use the previous formula with ut in place of u, and it'll fall right out. So the Laplace transform of utt is s squared times the Laplace transform of u, and then we have to subtract off the initial conditions. So s times u of x0 minus ux of x and 0. We'll do two more examples, both of them involving PDEs, and both of them will use the convolution of two functions, which I mentioned earlier in this lecture, and as I said, you've likely seen, but I'm not going to assume that. And even if you have, it's a good time to review. So the convolution of functions f and g, denoted f star g, is the integral from 0 to t of f of u times g of t minus u du. Now this is kind of a weird thing to think about, and it's hard to describe, so I'll do my best, and then I'll show you a nice little animation from Wikipedia. So suppose f of u is like this, say this is f of u, and suppose g is some other signal, maybe it's like that, g of t or g of u, doesn't matter what variable we use, then what we're doing here is we're going to, this g of t minus u, so we're going to flip this, we're going to deflect this horizontally, so we're going to move it like this, so reflect it across the y-axis, and then we're going to move it in this direction. Sorry, I'm drawing this really poorly. So this is g of t minus u. We're going to move it in that direction, and then we're going to integrate the area under the curve of this product. Okay, so that's hard to explain. Let me show you the animation. Okay, so here is the animation. So this first one, f of t and g of t, are both these little square wave signals, and we are moving g of t to the right. We're reflecting it, but that doesn't do any good because it's symmetric. We're moving it to the right. And this black line, and so the convolution is going to give by this black line, and it's the area of this yellow box as we move to the right. So I think it's best to just look at it and wrap your head around what it's saying. And then the next example is the same g, but f is now a little bit different. It's this signal here, so it's going to slice out a different area. Okay, so I'll let you go explore the Wikipedia page or other pages if you want, but I think a picture is worth 1,000 words, and an animation is worth more than that. Okay, let's move on. Here are some basic properties of convolution. The first one is perhaps surprising, because it's not at all obvious that if you switch the role of f and g, that you get the same thing. But the first one says it's commutative, f star g equals g star f. And the second one says that it's associative. So f star g star h equals f star g star h. Also not clear at all that either of these properties hold. Now we come to the convolution theorem, and this is why we really care. I alluded to this in the beginning of the lecture. If we have two functions, f and g, functions of t, then the Laplace transform of the convolution of them is equal to the product of the Laplace transforms. Now, if we take the inverse Laplace transform of both sides, then it follows that the convolution of f and g is just the inverse Laplace transform of the product. For now, let's keep this in our back pocket as a tool that we'll use fairly soon. We are now ready for our second example, which is our first involving a PDE. This will be on the diffusion equation on a semi-infinite domain. Remember, diffusion can refer to the diffusion of heat, which is the heat equation, or the diffusion of a concentration of a chemical. And that's what we're going to do here. So let U be the concentration of a chemical dissolved in a fluid where X is greater than 0. So that means the domain is the half-infinite domain, starting at the origin. And we'll consider the following boundary and initial value problem for the diffusion equation. So the PDE is ut equals uxx. We're going to assume that the constant c squared is equal to 0 to make things easier. We have one boundary condition because we only have one boundary. Remember that our domain is going to be, maybe this is a pipe or something like that. And the boundary condition says that for all time t, there is 1 unit of, what do you want to call it, of contaminant at this endpoint. So maybe I should sketch this as being up here schematically, even though the physical pipe is down here. And this is our initial condition that says that initially the entire pipe is free from the contaminant. So we have, think of it like this. There's fresh water in the pipe, and then for all time t, we have a leak of contaminant at the left endpoint. Finally, we should say that we are going to look at the solution where U is bounded, because what we're going to do is we're going to get two solutions. One of them will be bounded, one will be unbounded, and the one that's bounded is the one that's going to make physical sense. So that's the one that we want to focus on. Okay, so how do we start? Well, just like with the ODE, the first thing we want to do is apply the Laplace transform to both sides of the PDE. Let's think ahead a little bit. So we're going to apply the Laplace transform to the PDE. And then this initial condition doesn't involve t at all. So it doesn't make sense to apply the Laplace transform here. But this, the boundary condition, this does involve t. So we will apply the Laplace transform here. So starting at this one, we apply the Laplace transform. And we get that Laplace transform of ut, remember this is of x and t, is equal to the Laplace transform of uxx of x and t. Okay, so remember this turns t derivatives into multiplication. So the left-hand side is going to be s times u of x and s, and then minus u of x0, that's equal to 0. That's that fudge factor. And then the right-hand side is going to be uxx of x and s. Okay, so I'm going to drop these variables because I don't think we need them. What we have here is we have SU equals UXX. So this is now an ODE, a function in one variable. So how do we solve this? Psychologically, this is tricky because we're not used to S being the variable S being, in this case, it's a constant because our function, we only have one derivative here, which is x. So let me do this. Let me write, say, what if I had the same equation but involving y? So if this was the constant times y equals y double prime, then you could solve that. Let me write that as y double prime equals ky. For me, psychologically, even though these are the same, this is so much easier to look at than this. And we're assuming that k is positive, so this, you should be shouting sines and exponentials here. So let's write that down. So here, y of t would be c1 e to the square root of kt plus c2 e to the negative square root of kt. So that's basically what we have here, but instead of y, we have u. So let me just put this in parentheses because it's not really part of the problem. The solution here is going to be u of x, and now I will write x and s, although s is just a constant, it goes along for the ride. This is, so c1 times e, so instead of c1 I'm going to write a of s, because a, instead of a constant c1, this could be a function of s. So a of s times e to the minus root, not k, I'm sorry, I started to write k, s times t plus b of s e to the positive root s t. And yes, I did switch the order, I put the negative one first, and you'll see why shortly. So once again, it's a little bit distracting, but this is something we're used to. It's just the second order ODE, and the solution is a constant, and x is a constant, so some function of s times e to the negative root st plus a function, another function of s times e to the positive root st. Now, here I should point out the fact that this is bounded, and of these two functions, oh, you know what? I just realized I said t instead of, these should be x and not t. Sorry about that. So this is bounded, and one of these is bounded for positive x, that's this one, and one of them is not. So this is going to go to, we can get rid of that because, let me just write that down, because u of x and t is bounded. In other words, you can assume that b is 0. So here's what that means. That means that we have solved for u of x s, and it is a of s times e to the negative root s times x. Let me box that. So this is the Laplace transform of our solution. Let me draw a little diagram like I did in the ODE problem. So we started with a PDE, and we would like to find the solution, which is a function u of x and t. So what we did is we applied the Laplace transform, and instead of an algebraic equation, we got an ODE, and then we can solve, and the ODE we got was SU equals UXX. We can solve the ODE. We get that U of XS is, won't rewrite it, but this function here. And now what we have to do is we have to somehow invert this. So figure out what function, what unique function over here has this guy as its Laplace transform. So how do we do this? Well, there's not much we can do now. There's one thing we haven't used. Remember, we've used the PDE, we've used the boundedness, we've used this initial condition right here. We have not used the boundary condition. So let's use that boundary condition, and let's see how to do it. So what happens if I plug x equals 0 into here? Let's see what we get. So u of 0 s, so if we plug 0 in, the exponential is going to go away, and we're going to get a of s. Okay? Now what if we go up here and we apply the Laplace transform to this? So let's apply the Laplace transform to both sides. I'm going to use a different color because I can. I'm going to use red up here. So the Laplace transform of u of 0t equals the Laplace transform of 1. So the left-hand side is just big U of 0s. That's exactly what we have here. And the right-hand side, the Laplace transform of 1, that is, by definition, it's the integral from 0 to infinity of 1 times e to the minus st dt. And it's easy to check that that is 1 over s. If you've been dealing with Laplace transforms for a while, you probably have that memorized, or you can look it up on a table or something like Wolfram alpha. So that means that, so let me put a star here, this thing here is equal to 1 over s, and that's going to be by this star. So now we know what a of s is. A of s is equal to 1 over s. So that means that if we, the u of xs equals 1 over s times e to the minus root s times x. Now actually I should put this thing in here because that's the actual function. Before I didn't know what a was. Yeah, so this is the thing that we need to invert. And do you see how to do that? Well, this is where we use the convolution theorem. So we have a function which is a product. Let me call this thing f of s, and let me call this thing g of s. We know that the inverse Laplace transform of big F times big G is f of t convoluted with, I don't even know if that's used as a word, with g of t. So it's just the convolution of these two functions. Now, it's actually very complicated to compute the convolution of e to the negative square root of x, s times x. So instead, you can just plug this into Wolfram alpha. And if you do that, let me tell you what you get. It'll spit out something, it'll say ERFC x of x over root 4t. So this is called the complementary, that's a word I always have trouble pronouncing, ERF function. The ERF is the Gaussian error function. I think you saw this a couple lectures ago. Let me just give you an idea. Well, you saw something like this a couple lectures ago. It wasn't the same thing. So of course you know what the bell curve is. It's hard to draw, but it's something like this. And remember what the ERF function was, or the error function, is, so this is a function which is 1 over root pi from negative x to x of e to the minus t squared dt. So basically it's the area under the curve, the Gaussian curve from negative x to x. Think of it as the area under the bell, well, the entire thing is area 1. So what we're doing is we are excluding these extreme points that are below negative x or above x. So the complementary function is the area of the red parts. So this is actually equal to 1 minus the ERF function of x over root 4t. So once again, the ERF function is this blue area, and the complement of that is 1 minus the blue area, which is the red area. And that's all we're going to get. There's really no good way to simplify that beyond this. Let's conclude with a more general example of what we just saw. So once again, we have the diffusion, or the heat equation. And you can think of it as, again, an infinite bar that is 0 degrees, and then the endpoint is fixed at 1 for all time t. Or you can think of this as like a clean water pipe, and then there's contaminant right here for all time t. And again, you can draw it, if it's temperature, it's nice to draw it like this. You know, what's going to happen over time. This is going to get, it's going to get warmer and warmer at the end point, but it's going to get, I don't know, some intermediate time it might look like that. So it's up to you whether you want to think of this as the heat equation or the diffusion equation for a chemical. So here's the same thing, but the only difference now is instead of this being a fixed unit, either temperature or concentration, now it's some function of t. So it's going to vary with time. So maybe it gets stronger as time goes on, or weaker, or maybe it's a step function, or it turns off after a while. So this is obviously more general. So let's go through and solve this. I'm not going to go through every detail that I just did. I think I want to point out where the differences are. So once again, we apply the Laplace transform to both sides. And I'm going to skip most of the steps until we get to, let's go down to where we concluded that u of xs was equal to a of s times e to the minus root sx. So everything is the same up to this point. And now what's different is when we apply the boundary condition. So let's do what we did before. Let's apply the boundary condition here. So the Laplace transform of u of 0 t equals the Laplace transform of f of t. So this is big U of 0s equals big F of s. So as we did before, if we plug 0 into here, so u of 0s, the exponential goes away, and we get a of s. And again, this up here, the Laplace transform of f has to be equal to a of s. So this is equal to f of s, and that's from here. So the special case we did last time was when this was equal to 1, and the Laplace transform was 1 over s. So this is the more general form. So now we have our solution. U of x s equals the Laplace transform of f times e to the minus sx. And again, we have to invert this. So the inverse Laplace transform, let's compute that, or let's compute inverse Laplace transform of both sides. So the left-hand side, the inverse Laplace transform, is our solution, u of xt, which is what we seek. And then the right-hand side, the inverse Laplace transform, is the L inverse of f of s times this other function. Let me call this, I haven't used a g of s yet, g of s. So that g of s is, so that's that exponential. And of course, as before, the inverse Laplace transform is the convolution of little f of t, which is this unknown function. I mean, we're assuming it's fixed, with g. And what's g? G is, so the inverse Laplace transform of e to the negative root s times x. So if you go to Wolfram alpha and you compute what this is, so the inverse Laplace transform of this ends up being x, you don't want to do it by hand, x divided by root 4 pi t cubed times e to the negative x squared divided by 4t. So it's like a bell-shaped curve type thing in two variables. I think we saw something like this a couple lectures ago. And let's just leave this in the form of an integral, because that's one more thing that we can do. So this, by definition, is Well, remember the convolution is symmetric, so it doesn't matter which one we write as t minus u. So let's stick with this one as f of u. Doesn't matter. And then let's replace this function with, let's replace the t's with t minus u's and integrate du. So there we get x divided by the square root of 4 pi t minus u cubed times e to the negative x squared divided by 4 t minus u du. So here is our final solution for the heat equation on a semi-infinite domain with initial temperature or initial concentration 0 and boundary condition f of t. Now this is not the only way that we can solve this problem. Remember, we saw very recently that we could use something called the reflection method, and that also works perfectly well. But this is just an alternate way to do it. Okay, thanks for tuning in. Next time we will do a similar thing, but with the Fourier transform. And let me say a bit about this. The Laplace transform turns t variables, or turns t derivatives into multiplication by s. So it turns a PDE into an ODE by getting rid of the time variable. And similarly, the Fourier transform will turn a PDE into an ODE by getting rid of the spatial variable x. Now, one difference is time is typically assumed to be 0 to infinity, but space, not in this example, but in many examples, is the entire real line. Okay, so we'll do that next. Stay with us.